Okay, so solving a Winkler method question. Remember that in the Winkler method, it's a three-step reaction where the titration actually involves adding thiosulfate, S2O3 2-, and using that to figure out something about the concentration of oxygen, which was reacted in a previous step. So there's actually three different chemical reactions taking place in the Winkler method. But in the end, we talked about in class how if you match the coefficients, so I see that there's 2 MnO2 here, so I also want to have 2 in the next equation where it's used, so I have to double everything. We talked about how that water should have been a 2 originally. That was a typo, so now it's 4. And now I need to match iodine because that's the thing that's in both the second and third equations. So if that becomes a 2, this becomes a 4. All right, it's a little hard to see. This becomes a 4, 4, and 2. And so in the end, I can see that for every 1 mole of oxygen that's in my water, eventually that will lead to 4 moles of thiosulfate being reacted in the titration. So it's a 1-to-4 mole ratio in the Winkler method. So the questions are going to start by telling you how much of the thiosulfate was used in the titration. They have the concentration C, and they have the average volume used in the titration here. So we're going to start with N equals CV. So 0.001 and 0.028. That's the volume in decimeters cubed. So we get 2.80 times 10 to the minus 5 moles. It's the moles of S2O3. Now with that 1-to-4 ratio, I can see that the oxygen is going to be 4 times less. So if I divide that by 4, if I set up my ratio, 4 S2O3s make 102, or react with 102, I'm going to end up with 7 times 10 to the minus 6 moles of O2. So that's the answer to part B. Now I want to turn that mole amount into a concentration. The volume is 50 cm cubed and concentration is moles per dm cubed, moles per volume. So I just have to take the moles from part B and divide it by the volume in dm cubed. That gives me 1.4 times 10 to the minus 4 mole per dm cubed. So a very low concentration of oxygen, which is typical. And that's why typically this unit isn't used. Typically the unit is parts per million. The conversion from moles per dm cubed to parts per million is first to convert the moles to grams, and then the grams to milligrams. That's why in some cases, like down below, ppm is also equal to milligrams per dm cubed. So I'm going to take 1.40 times 10 to the minus 4, multiply it by 32, which is the molar mass of O2, and then multiply it by 1,000. That gives me 4.48 ppm, parts per million. So that is the value of the oxygen concentration in parts per million. The final question says determine the biochemical oxygen demand over the 10 days. It tells you that after 10 days they titrated and determined that there were only this many moles of water remaining. So you can do it different ways. You can take this value of moles, you can convert that into a mole per dm cubed and then a parts per million and subtract. That's fine, we can do it that way. So 5 times 10 to the minus 6, that's the moles divided by 0.050 dm cubed, and we get 1 times 10 to the minus 4 mole per dm cubed. Then to convert it to ppm, it's times molar mass times 1,000, and I get 3.2 parts per million. Okay, well, it started at 4.48, and now it's 3.2. So the change is what's referred to as the biochemical oxygen demand. That's how much oxygen was used up over those 10 days from that water. So the difference is 1.28 parts per million. This is the BOD, biochemical oxygen demand.